Hough transform is a feature extraction technique. It was developed to find imperfect instances of objects of a certain class. For example, here in these two images, we are searching for lines or for circles. So here the image that probably went through some edge detection is comprised of certain points. To our perception, some of the points are forming lines, but of course the points are not lying perfectly on those lines. And also here the points do not represent the perfect circle. So Hough transform enables us to search for instances of these objects that are not completely perfect, and also we can search for them in a very computationally efficient way. So first principle is that we use the search in a parameter space, or we perform the search in parameter space. The image space contains those points that we have seen, and in this particular example we will talk about detection of lines. So as we all know, through a certain point in space, for that point there is an infinite number of lines that can go through the point. So if we use some representation of a line like we have, for example, here, then we have infinite number of combinations of M and B that define lines going through a certain point. This, of course, doesn't mean that any arbitrary combination of these parameters will be suitable, that will describe a line going through that point. No. Here in the parameter space, where we have M and B on the respective axes, we can see that the parameters of lines going through the blue point are forming a line in the parameter space, and also the lines that go through the red point form a different line. And what we can see is that where those lines in the parameter space are crossing, this may be only possible for the combination of parameters M and B for a line that goes both through the blue and the red point. So if we would have more points on the same line, in the parameter space we would have a crossing of multiple lines. For the purposes of searching for lines, we use a polar representation of a line, which is more suitable, because with this representation we would have problems to represent lines that are perpendicular to the x-axis, that are parallel to the y. So here the line is described by two parameters, rho and theta, which is essentially the angle of the normal vector between the normal vector and the x-axis, and the length of the normal vector, or a distance, the perpendicular distance of the line from the origin of the coordinate system. So this way we can represent any line. Then the formula describing the line would be like this, with rho being the length of the vector and theta the angle. Okay, so what will happen in this example here? We have an image where we have only 3 points. Okay, so everything is equal to 0, just these 3 pixels have the value of 1, and to our eyes they lie on the same line, which is already drawn over here. But if we start to investigate which combination parameters fit to these particular points, then we will end up with curves like this. So for example, if we take this point, those combinations of theta and rho will be suitable for lines going through that pixel that lie on this curve. Yes, so we have 3 points, we draw 3 curves, and where the curves are intersecting, then there is the setting of parameters that are suitable for a line that goes through all 3 of these points. And by simply clicking on the image and reading out what the combination is, we can put it back into the formula and calculate the line and draw it. Yes, but here we are still in a real valued space, in continuous space, and searching for intersections of lines, it's not very efficient. Moreover, the intersection is appears only if there is a line going really through all the 3 points, which may not happen because, of course, any 2 points lie on a line, but a slight shift would lead the 3rd point out of the line. So we need somehow to accommodate the imperfections, and we do it, and we also get the benefit of finding the lines more easily by discretization of the parameter space. We simply do not allow any combinations of parameters, but we split the parameter space into squares. We can see like these small pixels are the small squares, and if the setting falls into the square, then we will say that the point was voting for this combination of parameters. We do it very simply. So we, for example, change for a given point the theta angle in discrete steps, and we calculate the corresponding rho, and if it fits into a certain interval of rho, then we increment that square by 1. What we get is, in this 2-dimensional parameter space, would be cells that received 0 votes, 1 vote, and over here we get 1, 2, or maybe 3 votes. 3 votes is the maximum because we have just 3 points. So the search for intersection is reduced to the search for the local maximum. Okay, but if we have more points, the situation is more complicated. So we have here an example. So here's an original image. We go through edge detection and we get this image, and we would like to find the lines that are in this image. So now we have great many points over here. All are lying on these edges, and so the parameter space will look more complicated. We have pixels that received 0 votes, 1 vote, 2 votes, maybe 30 votes, etc. Yes, but we can see here the local maxima. Yes, and the parameter space, because these sine and cosine functions are periodical, will be also sort of periodical, and these maxima and these maxima correspond to the same lines, just as if it would be turned around 180 degrees. So we can search for the local maxima using a very simple algorithm. We find a maximum of the entire matrix. Let's say it will be this one. And first what we do, we compare it to some threshold. If the line got enough votes, let's say the threshold will be 15, so if the maximum is above 15, we accept it as a line, and then we mask the entire neighborhood of this local maxima, which we mean that we set the values to 0. Then we search for another one, perform the same operation till we get maximum which is below our threshold. And for proper setting, it will end up like this. So we get 4 distinct lines that have received sufficient amount of votes. Okay, so we may right away see that the lines do not go straight to the points, and that's due to the discretization of the parameter space. That may look like a drawback, but in fact it's an advantage, because if those edges would be noisy, yes, the measure of discretization of the parameter space would accommodate for that noise, and we could find even in noisy environment these lines pretty well. Okay, the algorithm may be extended to any object that's describable by certain function, like for example by circle. Yes, so we can use it for searching for circles in an image, and here is a very simple example. We are trying to find all possible circles that are that may go through the points over here, which will correspond, like we take this point and draw a circle around it. So those will be positions of the centers of circles of given diameter that go through the point, and we find the local maxima which will correspond to the points that when you draw a circle around them you get 4 votes. Okay, so of course here the parameter space will be 3D if we search for circles of arbitrary diameter, and this problem gets more and more complicated the more parameters you need to describe the function. So it's not really useful for complex objects, but it can be very useful for simple objects like lines, circles, or ellipses. Here we have some examples of how it can be used. We can use it for vectorization of let's say buildings, to search for objects that are used like for centering of iris when we want to investigate let's say what the iris information is, or where the gaze is located, etc., etc.